Hi everyone, Mr. Ford here yet again. Today I'm going to go over the Chapter 5 circular motion problems. There were only a few of these, so I'm going to go over each one um, instead of waiting to see which ones you guys want to review, because you guys usually want to review a large portion of them, so I figured I'd have the time and make the video ahead of time. So the first one that we had to do was question 5, which is a level 2 problem, and we have a 0.55 kilogram ball attached to the end of a horizontal cord, and it's moving in a radius of 1.3 meters on this frictionless surface. So let's first sketch this out a little bit. So we have a ball, the mass is known, the radius is known. It's going to move in a circular path. And we need to find out how fast it can go before it breaks, knowing that the tension force will max out at 75 newtons before it breaks. So I just want to address, why is it on a frictionless table? That's just so that the string doesn't tilt downward, kind of like our flying pig lab problem where the pig was moving, in a horizontal circle, but the string supporting it was dipping down a little bit, so it added some other components to the problem. Here it's just something moving in a circle, so that's why it's on a table. So pretty simple here. We need to make sure that we state our Newton's second law for circles, or centripetal force equation. And then our centripetal force is caused by only the tension in the string. And we're going to look for that max force. So just checking out my pen stuff. So make sure you're taking the time to both state the general equation and then also the specific, naming what that centripetal force is. So we know that that force is going to max out at 75 newtons. We know our mass of 0.55 kilograms. I need to move my iPad because it's kind of messing up here. There we go. And we're solving for the velocity. Don't forget to take that square root in the end, and we have a radius. So plug that all in, and we get a velocity of about 13 meters per second. So level 2 problem, but not really all that difficult algebraically. So the next one we have, let's see, is number 7. Again, another level 2 problem. So we have a car driving straight down towards the bottom of a valley and up the other side of the road, whose bottom has a certain radius of curvature, 150 meters. And we're going to look at the very bottom, the normal force on the driver is twice his weight. What is the speed of the car? So they don't give us a lot of information. So first start off with a little picture. Here's our basic car, a box with some wheels. We see that our overall net force needs to be upward. Our radius of curvature, whatever that would be, kind of didn't leave room to make my circle, but so force diagram wise, and I'm going to draw a force diagram for this one just because the last one there was only one force involved. This one we have multiple. So we have gravity going down, and since the circle is above, our normal force needs to be greater, which we actually know that this is twice that of force due to gravity. That's what we're given. So we're looking to determine how fast it's traveling at the bottom of the hill, or not the hill, but the valley. So we make our general statement. Then our specific one, where we're going to have normal force minus force due to gravity, or we're summing the forces, so we're saying gravity is negative, so we're adding a negative. So just so that we're clear, it's not technically subtraction, it's summing the forces. So we don't really have numbers other than the radius. So what we can do here is we know that normal force, as we were told, was twice that of force due to gravity. The radius was 115. So still we cannot solve for anything numerically. But we do know Fg equals mg. So 2mg minus mg equals mv squared over our 115. And we start singing and dancing and saying everybody brought mass to our party. So mass is gone, and then we can now continue. So 2g minus g, that's simply just g, v squared. And I tend to, with book problems, write 9.8, just so that if you guys are using the solutions, that's what they typically do, and also use sig figs. So when we plug that into our calculator and take the square root because it's v squared, we get the velocity of our car being about 33.6 meters per second. So again, level 2 problem, a little bit more realistic of a level 2 as compared to number 5. The next one that we had is 8, right? Moving right along. And another level 2. How large must the coefficient of static friction be between tires and the road if a car is to round a level turn radius 125 meters at a speed of 95 kilometers per hour? So again, we're moving in a car circularly. Just draw a quick force diagram here. Normal and gravity are equal, and it's going to be force of static friction that is causing our turn. So again, we're stating our equation. Let's go ahead and determine what we have. Let's change colors because this has a lot of numbers in it. So we're given the radius being 125 meters, of speed or velocity of 95 kilometers per hour. So making sure our units match. So since we have newtons and there's meters per second hidden in a newton, and we also have a radius in meters, we need to convert this to meters per second. So you can either go through and do that by hand or simply do a quick Google search or use some kind of other app to calculate that in meters per second. I think that's all the givens that we were given. So it's our force of static friction that is our centripetal force, which from the fun equation, right, force of friction static is mu static times normal force. We can make that jump. And from our force diagram, we see that normal force is equal to gravity. And we know gravity, or force due to gravity, Fg equals mg. And yet again, we have another physics party where everybody brings mass. And we can take a little bit of mass from everybody. So right now you're thinking from that video, Everybody brought mass. It's going to get stuck in your head eventually. So now we have enough information to solve. So we're looking for mu. G is 9.8 meters per second squared. Velocity converted was 26.4 meters per second. And the radius was 125 meters. So plugging that all into a calculator, we would get mu to be about 0.57. So there we go for number 8. Moving along, we have 10, another level 2 problem, where we have a bucket. So you might have done this, in a backyard in the summer or at a beach or lake, where you swing the bucket of water around above your head, and if you go fast enough, the water does not fall out. So for part A, we have the mass of the bucket, the radius of the circle that it's moving, and when the bucket is at the bottom of this turn, the tension force is 25 newtons. So we're spinning this bucket around, and when it gets below, our hand is going downward, the tension is going to be 25 newtons. So we make our statement of circular motion. And for this specific problem, we have force of gravity down, and then tension going upward. That has to be greater because it's at the bottom of our turn. So we're going to have our specific centripetal force being the difference or the sum of tension and gravity, where gravity is negative. There we go. So we're looking to find the speed of the bucket. So we have tension being 25 newtons minus our 2 kilogram mass weighing, let me go ahead and use 10 here. It's an easy math. 20 newtons downward, 2 kilogram mass here. So not everybody brought mass to this party. We're solving for velocity and radius of 1.2 meters. So plug that all in, and we get a velocity of 1.7 meters per second. So when it's at the bottom. So for part 2, or part B rather, same scenario, but now we're going to look when the bucket is at the top of the circle so that the rope does not go slack. Slack means just there's no force on it. So we're looking to see, basically how fast can we spin this so that, we definitely are not going to get wet. Because if we go a little bit slower than this determined velocity, the bucket will start to fall, the water will start to fall. And as long as we go this speed or faster, then we are safe and dry. So what we're looking at is when that force tension is now going to be 0. So we're only looking at force due to gravity. So this is like part B here. And it's now at the top. So if there was tension, the tension would be downward. So same scenario, except that we only have gravity. Which was 20 newtons, 2 kilogram mass. And for this one, since tension is gone, we could make this a mass party one, but we already knew that force due to gravity, so it was okay just to put that in. But you can see up here, if we did mg, that those masses would cancel. So let's see, we plug that all in, and we get about 3.5 meters per second. And then I think we have one more left, maybe. Number 20. Yeah, that's our last one. Yet another level 2 problem. So we have a highway curve. So highway curves are marked with a suggested speed if the speed is based on what would be safe in wet weather. Estimate the radius of curvature for an unbanked, so this is a level, highway curve. So a lot of times they're banked, and the speed limit is 50 kilometers per hour. So the first thing, 50 kilometers per hour needs to be converted. So you can either do that by hand, from what you learned in chem and physical science and maybe in middle school. And we get our velocity that we're going to use, 13.9 meters per second. Then they're kind of mean and they make us go all the way back to the last unit, last chapter in a table. And they're not very specific. We're assuming a highway is going to be asphalt, and they don't have published values for wet asphalt in that table. So the closest thing, and actually some highways are made of concrete, sections of them. So we're going to use the mu value for static friction because we don't want our tires to slide, for rubber on wet concrete, which was 0.7. So a quick force diagram for our car or our tires, depends on how you want to look at it. With normal force, these forces are equal, and it's going to be our force of static friction that's causing us to turn. So we make our statement of circular motion, and our specific equation for this scenario where it's only static friction that's causing us to turn. And like an earlier problem, we're kind of looking at, the fun equation. Yet again, so force of friction is equal to mu normal. And normal in this case is equal to gravity. So when we talk about deriving equations, this is what we mean. We're not skipping step. We see that, eventually that centripetal force is going to turn into mu equals mg, but we want to take the time to indicate to our grader, to ourself, that the centripetal force is our force of friction. Force of friction is equal to mu normal, and that normal force is equal to gravity in this case. And then Fg equals mg, and that's where we see it is a mass party, so we can take mass from everybody. What are we looking for here? We're looking for the radius, so we can tell our engineers what to do. So mu was 0.7, 9.8 for gravity. Velocity that we're going to go around, that we're going to post, 13.9. Remember to square that. And we're going to solve for the radius. So we plug that all in, and we get a radius of our turn on our highway of about 28 meters. So that way we don't get sued by drivers for sliding off the road and crashing.